In this video, we'll be talking about X-rays from supermassive black holes, what they are, how we detect them, and why they're so essential for understanding the most powerful engines in the universe. We'll explore how X-ray astronomy allows us to look deep into the regions just outside the event horizon of a black hole, where matter spirals inward, releasing enormous amounts of energy. At the heart of almost every galaxy lies a supermassive black hole, often millions or billions of times the mass of the Sun. When gas and stars fall toward them, they don't disappear quietly. Instead, the infalling material heats up, forming a luminous disk that emits across the electromagnetic spectrum, particularly in X-rays. These systems are known as active galactic nuclei, or AGN. Some, like quasars, can shine brighter than their entire host galaxy. Gamma rays are key because they come from the innermost regions, just a few gravitational radii from the black hole. These high-energy photons are produced as gas in the accretion disk heats up through friction and turbulence. Above the disk sits the X-ray corona, a cloud of incredibly hot electrons. When ultraviolet light from the disk enters the corona, it gets scattered into X-rays through a process known as inverse Compton scattering. By studying the X-ray spectrum, astronomers can infer the properties of both the corona and the disk. One of the most important features is the iron K-alpha line, a narrow line at around 6.4 keV that becomes broadened and distorted by the extreme gravity and motion near the black hole. This relativistic blurring tells us how close the inner edge of the disk gets to the black hole, and in turn helps us measure its spin. A faster spin allows matter to orbit closer, producing stronger distortions. AGN don't just emit steady X-rays, they flicker. These rapid fluctuations, or variability, are a treasure trove of information. The randomness follows predictable patterns when analyzed statistically. For instance, the power spectral density, or PSD, shows how much variability happens on different timescales. We also observe time lags between different energy bands, such as hard X-rays lagging behind soft X-rays, indicating that fluctuations in the disk propagate inward and affect hotter regions closer to the black hole. Even more revealing are X-ray echoes. When the corona lights up, the disk reflects some of that light back toward us after a short delay. Measuring these reverberation lags lets us map the structure of the inner disk. These delays are often just a few tens of seconds for nearby AGN, indicating we're observing regions only a few light minutes across, incredibly close to the black hole itself. Another X-ray puzzle is the soft excess, a mysterious bump in the spectrum below about 2 keV. The origin of this component is still debated. One theory suggests it's due to a warm corona, cooler and thicker than the main one, that produces softer X-rays. Another posits that it's the result of blurred reflection from ionized gas very close to the black hole. Either way, it's a key feature that helps us understand how accretion disks behave under extreme conditions. Not all supermassive black holes behave consistently. Some undergo wild, dramatic changes. A tidal disruption event, or TDE, occurs when a star ventures too close to a black hole and is torn apart by tidal forces. The stellar debris forms a temporary accretion disk, producing a burst of soft X-rays. Interestingly, many TDEs lack a hard X-ray corona, suggesting different magnetic conditions than standard AGN. Some TDEs, however, do form a corona later, transitioning into a more AGN-like state. There are also changing-look AGN, galaxies whose black holes suddenly become active or go quiet over just a few months or years. They may show sudden increases in brightness, the appearance or disappearance of broad emission lines, and major shifts in their X-ray spectra. These events are thought to be linked to sudden changes in the accretion rate or disk structure, but their exact causes remain uncertain. And then we have quasi-periodic eruptions, or QPEs, a newly discovered phenomenon where X-ray flares occur regularly, every few hours, in the centers of otherwise faint galaxies. These flares are soft and short-lived, and they repeat with surprising consistency. One possibility is that they're caused by small stars or stellar remnants orbiting the black hole and interacting with the disk. These systems might also emit gravitational waves, making them prime targets for joint observation by missions like LISA in the coming years. All these phenomena are being studied with modern X-ray telescopes. Missions are giving us high-resolution spectra, while IXPE is exploring the polarization of X-ray light, revealing the geometry of the corona. Future missions, including AXIS, New Athena, and Lynx, will bring even sharper imaging, broader coverage, and faster response to transients. We're entering a new era of multi-messenger astrophysics. By combining X-ray data with infrared observations from JWST and gravitational wave detections from LISA and pulsar timing arrays, we'll get a complete picture of how black holes form, grow, and interact with their surroundings. X-rays are a critical part of that puzzle. They allow us to see what's happening right at the brink of the event horizon, to witness matter as it heats up, changes state, and ultimately disappears forever. Whether it's the steady flickering of an AGN, the sudden burst of a TDE, or the rhythmic heartbeat of a QPE, X-rays are telling us the story of black holes in action. Thanks for watching. If you enjoyed the video, don't forget to subscribe. As always, the reference material and article this content was based on is linked below.